Let's dive into the pretty amazing world of how computers are learning to see. We're going to pull back the curtain on how they find those hidden outlines in all the digital images that are, well, everywhere around us.
Yeah, it all comes down to this one fundamental process in computer vision. It's the secret sauce behind everything from your favorite selfie filters to the tech that helps self-driving cars see the road. And it all begins with finding the edges. So, what is edge detection? Well, at its heart, it's pretty much what it sounds like. We're teaching a computer to do what an artist does naturally: find the lines where one thing ends and another begins. It does this by looking for those sudden, sharp changes in color or brightness, creating a simple but absolutely critical map of the image. Okay, but it's not that simple. Before a computer can even think about tracing those lines, it has to deal with a huge problem: noise. You know, that grainy salt and pepper look you get in photos, especially when the lighting's bad. To a computer, every single one of those little dots looks like a potential edge. It's total chaos. So how do you solve a problem like that? Well, for a long time, the answer has been a really brilliant multi-step process called the canny edge detector. You can think of it as the classic go-to recipe for finding clean outlines in a messy, noisy world. After an initial cleanup, we'll get back to that, the canny method is pretty logical. First, it finds the gradients, which is just a fancy way of saying it scans the image for those sudden shifts in brightness. That's our potential edge. Next, it does something called suppression, which basically thins out those fat, blurry lines into crisp, single-pixel outlines. And finally, in a step called hysteresis, it connects the dots, cleverly linking strong edge lines to weaker ones nearby to create one beautiful, continuous outline. But here's the twist. That very first super important step, getting rid of the noise, it has a fundamental problem. The way it's usually done creates a huge dilemma that can actually mess up the whole process from the start. The classic tool that everyone uses for this cleanup job is called a Gaussian filter. Its whole strategy is really simple. It just applies a little bit of a blur across the entire image. This smooths out all that random noise, cleaning things up before the real edge detection starts. And this brings us right to the heart of the dilemma, and the research puts it perfectly. By blurring everything, the Gaussian filter doesn't just hide the noise, it also smudges the actual important edges we're trying to find. It makes them weaker, fuzzier, and a lot harder for the computer to see. To really get this, let's use an analogy. Imagine the image is a piece of land. It's got little random piles of dirt. That's our noise. And it also has these awesome steep cliffs. Those are our edges. The Gaussian filter is like a giant steamroller. It drives over the whole thing, and yeah, it flattens the dirt piles, but it also crushes those beautiful cliffs, turning them into gentle, sloping hills. But what if there were a smarter landscaper? Well, there is. It's an innovative new approach called the reverse transition weighting filter, or just RTW filter. And instead of that clumsy steamroller, think of this method as smart sandpaper. It is way more precise. So how does this smart sandpaper work? The RTW filter is incredibly selective. It's programmed to hunt for just those random little peaks and valleys or noise and smooth only them out. But when it sees a long, consistent slope of changing brightness, what scientists call a monotonic region, it recognizes that as a real edge and it leaves it completely alone. And check this out. This graph shows it in action perfectly. You can see the original signal has these two noisy bumps. Now, watch how the RTW filter completely flattens those bumps out. But, and this is the magic part, that steep, sharp cliff right in the middle, our edge, it's perfectly untouched. The noise is gone, but the signal is safe. Okay, so that's the theory, which is pretty cool. But how does it all play out in the real world? Let's put these two filters head-to-head with a really tough, noisy image and just see what happens. Our test subject is this picture of a colorful fish, and we've intentionally messed it up with a lot of noise. This is exactly the kind of messy situation where the traditional methods really start to fall apart. And wow, the results are pretty staggering. Look at this comparison. Sure, both filters get rid of the noise, no problem. But the quality of the edge is a whole other story. The Gaussian filter leaves the fish's mouth and fins all blurry, and you get a thick, weak outline. But the RTW filter, the features stay razor sharp, giving you a strong, clean, and way more accurate outline. The difference is just night and day. So the crucial point here, the big takeaway, is this. The RTW filter has this really unique ability to fight a war on noise while also acting like a bodyguard for the real edges. It keeps what the researchers call edge strength, making sure the important details don't get washed out during the cleanup.
And that leaves us with a pretty fascinating thought. This isn't just about getting clearer photos for Instagram. This is about giving computers a much more accurate way to see the world. So if we can teach them to see clearly through all that digital static, you have to wonder, what other faint, hidden outlines, maybe in medical scans or satellite images or deep in scientific data, are we now finally going to be able to find?